about curves and surfaces in 3-space as we go on trying to understand functions more. So I want to do a few more examples. Of curves. So we had circles, ellipses, lines, and my favorite, the cycloid. As I said a few minutes ago, you will get practice on the web work with figuring out some more parametric equations besides the ones you're doing for homework. I want to do another couple of examples here. So consider f of t is t squared, t cubed. So this is a curve that's a little more complicated than you're used to. But we can figure out bits and pieces of it and get somewhere here. For example, suppose I just looked at the first two coordinates. What is that going to give me?
Like a skewed parabola?
A who?
Kind of like a parabola?
Isn't it like identically like a parabola like?
Like x is going by
Aren't we looking at x is t, y is t squared?
Yeah.
So that's y equals x squared. Okay. So I'm going to try to keep this color-coded for when we put the picture together for 3-space. Okay, what happens if I look in the xz plane?
You get x cubed.
I have t cubed.
Like we know it.
X
X cubed.
xz.
Oh.
Like
Doing
we
the hard one.
like we know and love.
Sorry.
What do we love? Know and
It's
love?
x cubed like we know and love.
Do we know and love it?
Yeah.
Yeah.
Why are you so fond of it, Dan?
Because it's simple and in 2 dimensions.
What in calculus? This will come up later. But what significance did this curve have when you were in baby calculus? It's an example of, you have an inflection point here.
Symmetric.
It's an example where you have a flat tangent line, but not a min or a max, not a local min or a local max. That's why that's an important example in calculus. We will come back to things like that in a couple months. I know you're all waiting with bated breath. All right, now comes the fun one. What do we see in the YZ plane? We see t squared and t cubed. So if I draw y here and z here, so what do you notice about, what's true about t squared for all real numbers t?
It's always positive.
Always positive or 0. So I'm only going to be in the right half of the plane here, right? Y has to be non-negative. And z grows faster than y. So some of you were saying this is like z equals y to the 3/2. Is that correct?
Yeah. But it's always the positive one.
That only gives you the positive z's, right?
So
Take the 3/2 power of y, you're going to get a positive number. So what should I do? I should really do that. Agreed? So whatever the curve looks like, I need a new color, whatever the curve looks like here, so notice the derivative of this at 0 is 0. So it's flat. Doesn't grow quite as fast as y squared, but it goes faster than y, right? 1.5 power. flat tangent there, and then because it's absolute value, so you reflect it and you get a picture like this. And this is called a cusp. So this is called a cusp. It's a situation where you have two branches of the curve coming together with the same tangent direction. All right, put it all together. What does the curve look like in 3 dimensions? So what you want to try to imagine is a curve. So this is going to be x, y, z. You're going to have a curve in 3 dimensions whose projection into xy is this. So when you look from above, this is what you see. Whose projection into the xz plane is this. So when you project from this direction onto this plane, that's what you see. No, I did that wrong. No, I said it right. And then yz, when you project this way into the yz plane, you see this. At this point, you could give up and look at the picture in the book, which is drawn by a computer, and it does better than I can do.
Plot points.
Did you just draw the projection on it?
So I could actually put Mathematica on and take the time to project it on the screen for you. But let's see if we can roughly see what's going on here. So in the xy plane, I have this orange parabola. Right? So as t varies
Let's do 0, 0, 0.
from the negative numbers, it comes along like this and then comes along out here. Now, if I'm at a certain point here, then I want to go up from that x value to get to the point on that cube curve. So I'm going to have a point that is up here somewhere. And it's behaving according to this picture in the xz plane. Now, if I draw that cubic curve in the xz plane, I have to be a little bit careful because positive x's are going this way. So it's coming up in the positive x's, coming in flat, and then it's bending and going down below, back behind. For negative x's, as you go into the board, z is going down. So roughly what's going to happen here, and then if you project it this way, you're going to see that cuspal curve. You're going to see that curve that goes like this. And now the picture just becomes ridiculous.
Does that make sense?
So what it's sort of doing is following this orange curve, but it's going back down below underneath, back here. It's coming up, tangent here, and then it's twisting out and up this way. So back behind is the reflection of what it's doing in front. So it's coming down to the origin, and then you reflect across the xy plane, and you get the curve that goes behind, and then goes down below. So that's an approximate picture. Dan?
Could you think of it in terms of, and I'm going to use, pretty advanced terms for where we are, but in terms of 3 slopes? It's coming at me at this speed, it's going up at this speed, and it's going out at this speed.
So you're basically wanting me to do something which we'll do very soon, and take the derivative and say the velocity vector to this curve looks like differentiating component by component. And then you're saying as x moves at constant speed, y is changing at this rate and z is changing at this rate? Is that what you meant?
Kind of, I think.
So the xy slope would be the slope of this curve, which would be 2t.
Right, yeah.
The xz slope would be 3t squared.
Yeah, that's exactly what I meant.
Yeah.
Okay.
We'll talk a lot about velocities and physical interpretations of that as we go on. But this is actually an interesting curve, and those of you who at some point go on and take differential geometry will see this curve as sort of a prototype of what all curves look like locally if they have certain generic properties. Okay, that's enough 3D curves. That scared you enough. No, I'm not expecting you to draw these. But it is sort of fun to play with Mathematica and type in parametric plot 3D, and then you put t squared, t cubed, and you put t in some interval from like, say, -2 to 2, and you hit enter, and it draws you the picture. And then you can actually take your mouse and rotate it around and look at it from different angles, so it's sort of cool if you've never done it. And if you are wanting to play more with Mathematica, on my webpage is something labeled Mathematica Primer, and you can download it, and it will give you all sorts of stuff you can play around with. All right, I'm going to do one more example of a cubic before we go on. Suppose I write down this equation in the plane. Do you see why I'm saying it's a cubic?
Because x is cubed.
Highest degree of term appearing as a cube. Okay. What does this look like? No 3D stuff, just 2D.
This is where you start plotting points.
Yeah, we can plot points. We can also use our brains a little bit. But what point did you want me to plot, Dan? What's the most obvious point?
0, 0.
0, 0. What's another obvious point you want?
Negative 1, 0.
It's like 1 square root 1.
What's another thing that you learned to think about back?
Oh, sure. It's negative 1, 0, right?
Negative 1 is a root, right, of the right-hand side. So y has to be 0 there. Okay, what else do you notice about this? Thinking of symmetry. What does the fact that you have a y squared tell you, similar to what we were talking about in these pictures?
It's a cusp.
No, it's not going to be a cusp.
Like
But
cusp,
Y is always
positive, negative.
no, y doesn't have to
Oh,
always
yeah,
be
yeah.
positive. Y squared always has to
Yeah.
be positive. So this stuff can't ever be negative, which means you can't have anything to the left of x equals negative 1. There's nothing there.
So if you have a bubble, y-axis is going to be reflected.
That's what I wanted, Jonathan. You've got symmetry about the x-axis. Whatever x comma y you have, you're going to have x comma negative y.
Oh, yeah.
Everyone agree?
Mm-hmm.
So whatever I do, well, so when x is big, this term dominates, and it looks like y equals x to the 3/2 again. When x is big. So when I get way out here, it's going to be looking like roughly 3/2 power. What happens in between here and here?
It's like a little bubble.
Whatever happens here also happens down here, right?
Right.
So you come in, you come along like this, and then you flip over and you do the same thing, and it goes down like that. That's supposed to look more symmetric than it does in my picture. This is supposed to look perfectly symmetric, and it doesn't.
It's just the short one. That's the teacher.
Okay, roughly like that. Now, why should you have predicted what it looks like near here? What does this equation look like when x is near 0? Right? This term looks like what when x is near 0? 1. So it looks like,
X squared. Y squared equals x squared.
and what does the y squared equals x squared look like?
Y equals plus or minus x.
Y equals plus or minus x.
So it should just look like that.
So it should look like
there.
an x, right? And so if I had done this picture a little better, you would have seen the x if you looked at the tangent lines there. Okay. This, I told you this was called a cusp, a curve that crosses itself in two different tangent directions. The fancy word for this is a node. Two different crossing directions. All right, let's try to parametrize this thing. So there's no reason that you should have thought to do this, but if I tell you to do it, you should be able to follow my directions. I want, for our t value, I want t to represent, so I want to write f of t again, right? And t, I'm going to tell you, represents the slope of a line through the origin. So in some of the homework you're doing, there's problems where it tells you specifically, let t be this thing in the picture, or let t be the angle through which something has turned. I'm telling you here, t should represent the slope of a line through the origin. In other words, I'm going to take a line through the origin that has slope t, and I observe that it intersects the curve where? At the origin.
T squared?
No, it won't be tt squared. But it also intersects the curve somewhere out there. In a unique point, actually, other than the origin. What happens as t gets bigger? Well, I get further up here. What happens as t gets smaller?
Eventually, it's intersects.
When t is 1, presumably I'm going to get just here. I'm going to be tangent there. But what happens when t is negative? I mean, sorry, smaller than 1? You get a point over on this piece. And as you keep, when t is 0, you're here. When t now goes negative, you swing around here for a while, and then eventually you come back down and get points over here. Yes, sir, Matthias.
Does this come from like the interpretation of like the graph of f of t?
No.
Okay.
No, because that would be in 3D.
Right, it's just, okay.
It's just, I'm saying, because this is actually a little bit of introduction to algebraic geometry, which is fancy and you don't need to worry about it, but because this is a cubic equation, you expect that if you draw a line, it should meet the curve at 3 points. Because if you substituted the equation of the line in, the cubic would then give you a cubic in t. Well, 2 of the points of intersection are here, so the remaining point is going to be parametrized by that variable t. That's what's going on here. So let's just do it. How do you write the line with slope t? Y equals tx. Let's take this equation and substitute in y equals tx. What do I get on the left-hand side?
T squared, x squared.
So you see here that I have x equals 0 as a solution. If I throw out, in fact twice, it's a double root. If I throw out the double root x equals 0, what am I left with?
T squared equals x plus 1.
T squared equals,
X plus 1.
so what's x?
T squared minus 1.
T squared minus 1. I got x.
But then you can also factor.
What's y?
T times.
Yeah. Right, we said y was tx. Well, that wasn't so hard, was it? So my parameterization is t squared minus 1 and t times t squared minus 1. And that's going to give you all the points on the curve. Notice that as I predicted, when t is 1 or negative 1, what happens?
It's the same.
Those are the lines that are actually tangent to the curve at the origin, and you just get the origin as the intersection point. So this actually covers the origin twice. But other than that, it gives you every point on the curve once. And that makes sense, right? Because if you're going to come from here and get over here, you have to go through the point at the origin.
Likewise.
And then when you come back around here, you have to go through it again if things are going to be continuous.
How would you know to make t represent the slope of the line?
That's right. Remember, I prefaced it by saying I would never expect you to come up with it, but once I tell you, you can do it.
Okay.
Someone told me to do this when I was roughly your age, and I've never forgotten it. So that's how I know.
So we should listen to you, is that what you're saying?
No, I would never say that. All right, so that's my examples of curves. What I really want you to do is get practice, as in the problems in the book that you're doing now, and then with more on web work, actually just taking things that are built out of pieces and saying I can get from here to here by following these vectors and adding them. I'm going to give you one problem on the written homework next week that's similar to this, where I tell you, here's a picture, parameterize it by using t to mean blah, and figure out the equation. So you'll have a problem like this. Okay. So on to functions from R2 to something. On to. Two separate words, not TO. Now, so we've been talking about R to R1, R to R2, R to R3 so far. Now I want to do R2. I want two independent variables. And rather than start with something hard, I'll start with something easier for today. And then tomorrow we'll talk about R2 to R2 a bit. So how should we understand functions from R2 to R? So for example, if you're an ant that lives in the plane, the function f might be the temperature you feel as you walk around on the plane. So e.g., temperature of a 2D ant. If we were doing a function from R3 to R, we might think of our R3 as where we are in space.
It's like a fly in the temperature.
Like now it would be the temperature of the fly. Or the way I feel with the weather being the way it's been, the three-dimensional flying cockroach. Come collect them from my house anytime you want. So you can visualize higher dimensional functions with a higher dimensional domain in lots of different ways, and we're going to actually use the temperature model a bunch as we go on, just because it's a good example. I might actually make a fly be a bumblebee at some point later in the course rather than a fly.
Okay, all right.
So how should we visualize functions of two variables?
Well, if you're transferring it from two variables to a, well, if you're transferring it to R, you could see it like as a 3D graph with.
Good. So one approach would be to look at the graph. Remember we talked about the notion of a graph yesterday. We can look at the graph of f, and that's going to be the set of points in R2 plus 1 that look like x, y, and then f of x, y. So this is the kind of schematic picture I was drawing you yesterday, where you think of the domain as being here, and the range as being the vertical axis, and you plot for every point x, y in the domain, you plot the point at height, the value of the function. So the function is representing the height over the xy plane, just like you were used to with y equals f of x, where the y was the height over the x-axis. Now there's,
Since temperature, can we also do like contour plots,
Ah.
things like that?
okay. Another thing that we're going to look at, as Taylor is saying, is if you look at a weather map, and you're interested in barometric pressure or temperature, you don't see graphs, because that would be too hard for most people to interpret. What you see, I'm not good at drawing the United States at all.
Just takes practice.
Not bad.
I couldn't see.
Boy, that's, Florida's way too big.
So is to do with it.
Well, if you exactly, the one thing that you need to remind you of, Oregon and Maine, they're on the
and
same.
Montana.
Maine, top of Maine, or the top of Oregon.
It looks like a Nintendo 64 controller.
All right,
Mostly flat.
Hey, that's pretty good.
I'm not a geographer.
It's like
I
spending a
have
lot
one
of
in my
time on
other
the left
class, I'll
side.
have
and
him come in and do it tomorrow. If you look at a map of the US, say, and what you see if you look at a weather map is they've drawn things that look like this. What do those represent? Isotherms. So therm is temperature. Iso is Greek for same. You can also see a map with barometric pressure, and that's isobars. So these are curves that are representing constant temperature values, and they're showing you the set of points where it is, for example, I don't know, 85, and where it is 75, and where it is 65, etc. Now, so you can do this in higher dimensions as well, and we'll talk about that in a few minutes. What are you also used to seeing, and we'll come back to this, by the way, later in the course. If you're going hiking and you get a topographical map, it's not showing you temperature. What is it showing you when it draws curves?
Elevation.
Elevations.
Right.
So a typical map that's useful if you're going hiking is a map that shows elevations of where you're going to be. And then one thing we'll talk about a lot when we get to chapter 3 is if you want to go hiking and you're interested in hiking up the steepest trail possible, how do you see what that is on the map? So we'll come back to that. All right, so I want to do some examples here where we look at both these. So as Taylor said, this is often called, these curves are called level or contour curves of f. I don't know why contour. level curves. They're showing you the curves where f is constant, has a certain level value. So I want to just do a few examples here, just so you start getting used to this. So let's do something easy to warm up. So in vector notation, I'll write f of vector x is magnitude of x. That's the formula in terms of standard xy notation. So I want to do two things. I want to plot the graph, and I want to plot level curves of f. And I want to discuss how the two relate to each other. So what the graph is going to be a 3D object. The level curves are going to be drawn in the plane, in the domain.
Yeah.
So let's think about level curves of f. What values does f take on in the first place?
Greater than 0?
Greater than or equal to 0. 0 is not too interesting. Where is it 0?
It's 0, 0.
Okay. Where is it 1?
Unit circle.
Unit circle. That's terrible. It's harder for me to draw small circles than it is to draw large circles. Okay, I'll label it with a 1. Where is it level? Where is it 2?
Bigger circle.
How much bigger?
Square root of 2.
The
Twice
circle with
as
the
big.
radius.
I say it right. Did I say square root of 2? Is that correct? Square root of 4? 2.
If f of xy equals 2, what does that say magnitude of x is?
2.
2. So it's a circle of radius
2. 2.
3.
3.
So what you're seeing is evenly spaced level curves if you increase the value at an even rate. Okay? Now let's draw the graph.
Isn't it just
like a
an
bowl,
upside
right?
down
Yeah.
cone?
And you have it reflect.
Whoa, 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 whoa. Nobody heard that. What did we say the smallest value of the function was?
0.
So doesn't the graph start at the xy plane and go above?
Yep.
Yeah.
There's no negative z values. All right? Now, what's the graph going to look like?
It's an upside down cone.
Some people,
It's an upside down cone because it just has like circles of greater.
it's actually going to be a cone.
Right, because it's going out constant.
So the first thing I want you to think about here, and this is going to come up throughout the course, but I want you to think about this, is think about symmetry. As you go around the origin, as long as you stay the same distance from the origin, the function doesn't change. So this is symmetry about the origin. If you have any point that's a certain distance away, all the points that same distance away will have the same function value. So whatever the function's doing at this point, it's doing the whatever the height is over here, it's got the same height at all the points that are the same distance from the origin as that point is. In other words, if I go a distance 1 here, then the value of the function is 1, and everywhere on a circle, I'm at the same height, if that circle's centered at the origin. So that, what I'm doing here is I'm lifting this level curve up to height that it lives at, namely 1. Then, I'm lifting this level curve to its height, which is 2.
happened too, so it's.
And I'm lifting the blue level curve to its height, which is 3. And that's a very big level curve. So it's sort of like if you were good with your hands and you knew the level curves, you knew the isotherm map. If you used paper mache or something, if you were a better engineer and artist than I am, you could construct the graph physically by taking these curves and making a surface whose slices at those heights are given by these curves. So now what shape are we seeing here? Well, my drawing hasn't been perfect here, but Dan mentioned the word slope. At what slope am I going uphill here?
1.
1, right? You go up a unit for every unit you go out. So I should see a line with slope 1 that represents how I go up. And in fact, if you look at this thing in the plane where x is 0, so it's like slicing and taking x equal to 0 and taking whatever surface I have and slicing it. What do I have here? Square root of?
Y squared, which is just y.
Be careful.
Plus or
Plus or
minus.
minus.
No,
Just
just positive.
No,
Absolute
say
value
it
of
right.
y.
What is the square root of somebody squared?
Absolute value.
Absolute value. So if I graph the absolute value function in the yz plane, and then say I have symmetry as I rotate around, what do I get when I rotate that line around the z-axis? I get a cone. And that's the graph of the function. And then similarly, having started with the cone, if I start with the surface and slice it, I recover the level curves that I plot back down the plane. Okay. Any questions on this?
Where does the height of the level curves come from?
The value of the function. So I look at levels where this equals whatever. So if I look where this equals 2, I'm looking at the set of points x, y where square root of x squared plus y squared equals 2. And that's the circle radius 2.
Right. And then where it comes on the z comes from.
That is the z.
That is.
So these become the z values when I do the graph.
Okay.
So this point, these points are lifted to z equals 2.
Okay.
These points are lifted to z equals 3. Sammy?
So, when you say f of vector x has components x and y.
Right.
Okay.
It's in the domain, so it's just in R2. All right, so slight modification. I'm going to keep symmetry, but I'm going to change the problem. This is still going to be symmetric about the origin, but what's the difference going to be now?
So instead of absolute value, it's going to be a parabola.
Now you're going to get a parabola, right? If you now think about a cross-section where you set x equal to 0 and look at in the yz plane, you're going to get a parabola,
The YZ plane being the one that,
this plane. X is coming out of it.
Right,
so
okay.
It's easier for me to sort of
Right.
think of slicing it that way.
right, okay, that's right.
So what do you think the shape is going to be now?
A bowl.
Now you get your parabolic bowl. So now if I draw my graph, I'm going to take y squared, z equals y squared, and then spin it around the z-axis because of my symmetry. Right? It says all points at the same distance from the origin are at the same value for the function. So now I'm going to get circles still when I rotate around. What's the difference, though, between this function and this function? So if I now draw the level curves, let's try to color coordinate the way I did before.
Take it farther apart.
So at height 1,
The level curves get closer together.
I'll have my orange circle, and it will have what radius? At height 2, I'll have a circle. What radius? Square root of 2. So instead of being at distance 2, here I'm at distance square root of 2. But that's the 2 level curve. What about 3?
Roughly 1.732.
Blue.
It'll be the square root.
And finally, if we get to height 4, what's the radius of my circle?
2.
My picture is not perfect, but you get the idea. You still get circles for your level curves. That represents the symmetry of the function about the origin. But you see that for moving a certain distance here, you've climbed a lot higher on this surface. So if you were on a mountain doing this, I wouldn't like to be hiking on a mountain of a shape quite like this. I'd rather turn it upside down. We'll get to that later in the course. But if you were hiking on this, you'd be changing your elevation a lot more quickly if you walk with the same horizontal distance, right? That's because y equals x squared, or z equals y squared, grows a lot faster than a line z equals y does.
So will we see that from using because like you can see that from just analyzing y squared equals or x equals y equals x squared, like you can see like how the derivative change
Sure.
becomes much faster. Will we also see that in like 3-dimensional?
Yes, so we will be getting soon to calculus with more than one variable and understanding the rates of change in various ways. Now, what about an example that's not got all this symmetry to it? Suppose I looked at a function
Is that it?
Mm-hmm. Well, it is easy, but, so what are the level curves going to look like for this? What about 0?
0.
No,
Well, there goes my thought.
It's going to be more than 0.
it's going to be more than 0.
There's gonna be a line.
It's going to be a line, x plus y equals 0.
Right.
Wait, for 0, are we saying like just setting one of those variables?
No. So if I'm doing level curves, I'm setting the function equal to that constant and saying, what are the set of points?
Gotcha.
What is the set of points for it? What about x plus y equals 1?
It's gonna be
So
shifted.
slope of
This is like what we were talking about yesterday, where we were shifting a plane. Well, now we're shifting a line, right? Parallel, but at a further distance from the origin. And then 2. But now it would be interesting to also have negatives in there, right? So -1 would be down here. -2 would be down here, and so on. What's the graph of this going to be?
diagonal plane, I think.
Yeah.
Yeah, it's gonna be planes.
Well, now you don't have rotational symmetry, so now you're going to have to be a little fancier, right? So if you wanted to look at where x is 0, you would see z equals y. Just doing that with yellow. So you would see z equals y, which I'm going to tilt slightly more to see the picture a little better. And then what would you see if you set y equal to 0? So in this plane, you're seeing that. In this plane, what are you seeing?
Z equals X.
You see z equals x. So it's going up at the same rate in the x direction. In the plane y equals 0.
Like this.
But of course, it keeps on going, right? Down here, down here. So if you actually took
It's the span of those two vectors, or
If you
those
took
two.
the span of those vectors, you would build the plane,
Then just
because it's linear. So you can imagine colors here. You can imagine a plane that's built out of this, that's coming out at you. Watch this. And if you slice the plane at various heights, you should see these lines lifted up. What about this is going to be one of my favorites, as you will see during the semester. So what do you see now for the surface? If you fix x equal to 0, you see z equals y squared. What if you fix y equal to 0?
we see the negative.
So in the xz plane, you see a parabola going down. What happens if you now do y equals 1? If you move over here to where y is 1, well, you see the same parabola going down, but it's shifted so that its vertex is on the green curve. Right? This is where y is 1. This is z equals 1 minus x squared. If you go to y equals negative 1, you see the same parabola there. You go to bigger y's, you have parabolas shifting up and over. If you shift it out, you would see to where x is 1, what would you see? You'd see y squared minus 1. You would take this parabola that shifted down so that it was going through that point.
So it's kind of like a Pringle?
It's not quite a Pringle, but it's called the saddle surface.
Ah,
Because it's the shape you would imagine a saddle being on. Your legs go down here and the saddle goes up.
it's the Pringle.
You'll see a monkey saddle later in the course for monkey. What do you think's different?
Smaller.
It's made for monkeys, but what do monkeys have that we don't?
Tails.
Tails.
It's got a hole in it then.
So you need a place not just for your legs, but for the monkey's tail. Now, what about the level curves of this? So imagine now that you come along and slice it and say z equals 1. What do you see? You see y squared minus x squared equals 1. That looks like this. What if you slice it at negative 1? So in this picture, the hyperbola you just told me to draw looks like this. What happens when I slice down here? It's the opposite. It looks like this now. What happens in the middle as you raise this? So here the hyperbolas are coming out this way. Coming out at you here and behind back there. What happens is you raise the plane just to the origin.
Angles.
What do you get when you set this equal to 0?
X equals y and x equals negative
You
y.
get x squared equals y squared. In other words, we're back to our x again. And in fact, I will let you go home and visualize this. If you slice this plane here, it's actually what we'll find out is called the tangent plane to the graph. And it intersects the graph on exactly those two lines, which become the asymptotes for these families of hyperbolas.
Yeah, makes sense.
Okay, so tomorrow we're going to talk a little bit about maps from R2 to R2, and then we're going to start moving our way to understanding what it takes to understand limits. So we're going to start talking about things like balls and open sets and closed sets.